I'm Meghamala from Electronics and Communication Department, IARE Engineering College. I'm here to discuss a few topics on digital design through Verilog subject, from the subject digital design through Verilog. So let me go forward. And here the introduction part, the very first part from the subject digital design through Verilog is introduction to Verilog. And here we have few topics to be covered in the unit 1, as this is a unit 1, and we have Verilog as HTL, popularity in Verilog HTL, model concept, modeling styles, and comments, identifiers, keywords, and value sets. And the other section consists of data types, operators, data flow modeling, delays, and examples using modeling. And also we have memory elements as well. So let me go forward, and here the basic objectives and outcomes of this particular unit is the object is to make the student learn and understand to make the students learn and understand the things, that is acquire a basic knowledge of Verilog HTL and the language constructs and conventions in Verilog, basic concepts in Verilog, data types and parameters, and compiler devices. Whereas the outcome after learning, like the student will be able to define the basic terms in HTL, and also the students may remember data types and operators, and as well the students remember test benches for simulation and verification. So here are the basic the objectives and the outcomes of this particular unit. And whereas we go into the topic itself is the very first topic from the unit is Verilog as an HTL. So basically, what is a Verilog? So Verilog is something that it is aimed at providing a functional, tested, and a verified design description for the target FPGA and ASIC. So as we discussed, like it is aimed at providing a functionally tested and verified design description. So design description for the target FPGA, that is field programmable gate arrays and ASIC. So it provides a functionally tested and also the verified verification for the target field programmable gate arrays. And also in the beginning, if you recollect, the designs involved just a few gates. So in the past years, the designing of the chips, they involved just a very few gates, and thus it was possible to verify these circuits on paper or with board. So as in the beginning, we said like the construction of a module consists of like very few gates. So whereas in this and it is easy to verify whether the errors are there or not. It's very easy to verify the errors are present or not. It's verify the errors present or not is easy to verify on paper with board. And also, as a designer grew larger, so as the years are passing, the designers grew larger and more complex. Designers began using gate-level models described in hardware descriptional language to help with verification before fabrication. So, as the years are passing, what the inventors or else the designers, what they did is they have grown. That means they have developed various modules where more complexity. The complexity will be they minimize the complexity, and the designers began using gate level models described in hardware description language. In this hardware description language, basically the designers were used many number of, like using gate level models. They have designed the models. They have designed the different modules to help the verification before fabrication. And also, when designers began working on 10,000 gates design, these gate level modules were too low level for initial function specifications and early high level design exploration. So this sentence is talking about when the designers began working more than 10,000 gates. If for suppose if a module to design a simple module we may require 2 gates or 3 gates or a minimum of 10 gates or 100 gates. But when it comes to design a complex module, we require more number of gates that may go to 10,000 gates. So when the designers began working on 10,000 gate designs, these gate level modules, so as the module is being designed with the help of a gate, so we call it the gate level module. So this gate level module is where too low level for the initial function specification and early high level design exploration. So as the gates are increasing, but still the complexity maybe decreases, because the specification that the modules that we are using here is the gate level modules. And also, an HTL is not a software programming language. So basically, this topic is all about the Verilog, and we are using the HTL language. So this HTL, hardware description language, basically it is not a programming, it is not a software programming language. So HTL, what is HTL mean? HTL is all about, it is a specialized computer language. It is a specialized computer language used to describe the structure and behavior of electronic circuit. So here, this sentence is specifying us very clearly regarding the HTL. So HTL, hardware description language, we are saying that it is not at all a software programming language, but it specifies, or else it specializes a computer language. It specializes a computer language used to describe what? We have to describe the structure and behavior of the electronic circuits. So in general, we all know what are the electronic circuits. We have different types of electronic circuits, right? Like multiplexer, decoders and encoders, and also the gates and various types of modules used for the communication purpose, and all these things, all the circuits, all the electronic circuits, just to describe the structure. To describe the structure and the behavior of that particular module, we are using a specialized computer language, that is nothing but a hardware descriptional language. So it is very important to be remembered that HTL is not a software programming language, but it is a specialized computer language where to describe. So here, as it is a specialized computer language, we have to describe the structure and behavior of the electronic circuits. So most commonly digital logic circuits. So you all know what are digital logic circuits. And coming to the levels. So here in this Verilog as an HTL, we have different levels of description. So what are those? First one is a gate level, second one is a data flow, third one is behavioral level, and the fourth one is circuit level or switch level. The another name for circuit level is nothing but the switch level. So these are the important levels to design a module based on the HTL. First one is the gate level, second one is data flow, behavioral, and the switch level or else the circuit level. So coming to the level of designing description, as I said the hardware description language is not a software programming language, but it describes about the structure and behavior of the circuits. So here we see what is a software programming language in basic. So this language which can be translated into machine instruction and then executed on the computer. So here you have to you have to ponder on two things. What is the software programming language and the hardware description language? You have to know the similarities between these two languages. So as we said, software programming language, it is nothing but it is a language which can be translated. It can be translated into machine instructions, and after translation into machine instructions, after getting the instructions, and these are then executed onto a computer. These are nothing but the software programming language. Coming to the hardware description language. So what is a hardware description language? As earlier we have discussed, hardware description language is all about the designing of a module based on the structure and behavior of the circuit, digital circuits, basically logic circuits. So here the hardware description language, it is a language with syntactic and semantic support for modeling the temporal behavior and spatial structure of hardware. So here in this hardware description language, you have to remember an important point is the language itself is a syntactic and semantic support. That means what here this language consists of some syntax. The syntax based language, it is a syntax based language where support for modeling and temporal behavior and spatial structure of the hardware. So it's all depend the structure and behavior of a particular digital circuits will be mended in terms of the temporal behavior and structure, spatial structure of the hardware. And also a Verilog includes a model name, and an interface in the form of port list. So as I said you, this hardware description language consists of, as it is a semantic language, it consists of a syntax. That means all the modules will be written in a syntax formation where it includes a model name. This model name, the syntax will include a model name and an interface, and in the form of, it should be in the form of port list. So what is this port list, what is this interface, and what is this model name, we'll be knowing in depth in the coming slides. And also coming to the next point, a module can contain other modules through model instantiation, creating a module hierarchy. So as I said you, this hardware description language is totally a syntactic and semantic language which supports the modeling of temporal behavior. So as it contains a different, some circuits are complex and some are very simple. So for this complex circuits, we need more than one or two modules. So for each module, there is a syntax to be written. That is all about the HDL language. So here it is. So this sentence is talking about a module can contain other modules. So a particular module we are talking about, for example, this module 1. Indeed, this module 1 consists again a module 2. So it means that we can have more than one or two modules in the hierarchy form. That means a module can contain other module through instantiation. So that means what, if we if we have three modules, module 1, module 2 and module 3. So how we are representing these modules? That means what, we are representing the basic module as module 1 and the pre-module as module 2 and in the pre-module as module 3. So that means what, here the module can contain other modules as well through module instantiation and creating a module hierarchy. That means what, we are initializing the name of the modules through hierarchy form. That is module 1, module 2, module 3. Module 1 is a basic module, module 2 is a secondary one, module 3 is a third, tertiary one. So this is nothing but a module hierarchy. So here in this particular figure is talking about the levels. So here as I said, we have three levels. One is behavioral, data flow and gate level. So we'll in depth we'll discuss what is behavioral model, what is data flow and what is gate level. So coming to the behavioral modeling. What is this behavioral modeling? Behavioral modeling, these modules, high level algorithms is implemented with little concern for the actual hardware. So this behavioral model, it talks about the modules with high level algorithms. So here in this behavioral model consists of a high level algorithms. They are implemented with little concerns for the actual hardware. So with the actual hardware, the algorithms which are present in the module in order to represent the structure and the behavior of a particular module, the thing we have to remember is in this particular behavioral model, the concern is to be actual hardware with high level algorithms can be seen. And coming to the data flow level, in this data flow level, the module is implemented by specifying how data flows between registers. As I said this HDL language, this HDL hardware description language is nothing but it is a language where we can design and fabricate the modules based on the structure and modules based on the structure and behavior. Based on the structure and behavior. For example, and all this happens in the digital circuits. Digital circuits. So as I know, the digital circuits are many different types of digital circuits we have. Like the basic digital circuits I can say is a storage devices like flip-flops, latches. You all know what are the flip-flops and what are the latches. They are the 1-bit storage devices. They store only 1 bit of information. It could be either 0 or 1. The digital circuits, it takes only the information in terms of zeros and ones, isn't it? So here this data flow module, this data flow level, it talks about the module is implemented. The particular module is being implemented, specifying how data flows between the registers. As I said if we have consecutive registers R1 named R2 and R3, if you have 3 registers and the data flow between these 2 registers can be implemented using the data flow level. It is very simple as such. See, for example, I have in my register I have the data as 0. I need to transfer from register 1 to register 2. So which level can I go for? I can prefer this data flow. Using this data flow, the module can be implemented by specifying how data flows between R1 to R2 and how the data flows between R2 to R3. Okay, and next coming to the gate level. As the name indicates, the gate level, the module is implemented in the concentric logic gates and their interconnections. As it is a gate level, the module is in concentric logic gates. You all know the logic gates, right? You have studied in the previous sections, previous classes. What are the logic gates? Logic gates are nothing but the storage devices. They store the information, right? So this logic gate, we have universal logic gates and the normal logic gates. NAND, for example, AND, OR, NOR, NOT, AND, NAND, and all this. Isn't it? These are the gates. So this gate level is implemented in terms of concentric logic gates and their interconnections. Okay, you see here, this is a circuit level or switch level. Coming to the circuit level or switch level, as it is one of the level in the HTL, in the Verilog as an HTL. So this is talking about the circuit level. Another name for circuit level is switch level. So what is the circuit level? At this circuit level, a switch is a basic element in which digital circuits are built. So as here it is, the name indicates, this is a switch level. So the switch is a basic element with which the digital circuits are built. So most of the digital circuits in this particular level, most of the digital circuits can be built using the switch base. So we are calling it as a circuit level or switch level. So coming to the next point, switches can be combined to form inverters and other gates at the higher level of abstraction. So here this sentence is telling us about the combination. It can be combined to form inverters. Okay, and other gates at the next higher level of abstractions. Only at the next higher level of abstractions, we can see switches can be combined to form inverters and also the other gates. As I said and for example, we have AND gates. How could it be turned into NAND gate? If this is the AND gate, AB is the input, Y is the output. So AND gate would be, NAND gate would be, this is an AND gate, isn't it? So here you can see some inverters. So switches can be combined to form inverters and other gates at the higher level of abstraction. So here if you see this particular figure, this is talking about how switches can be combined for the inverter and for the higher level of abstraction is this is, here we have input and we have output Q1 and Q2 and VCC. So here the output of Q2 is directly given as input, and from here we can take the output from the here onwards you get the output by giving the supply 0. Okay, this is all about this switches. So this and coming to the gate level, this gate level is another level in the HDL, Verilog as a HDL. So at this at the next high level or abstraction, design is carried out in terms of basic gates. So as the name indicates, the gate level, the designing of the modules can be carried out in terms of basic gates. So all the basic gates are available as ready modules called primitives. So we'll be storing all the gates in the when it comes to the syntax, when it comes to the language in the HDL, all the gates will be stored in the module ready modules called primitives. So this is a basic AND gate. So you all know what is an AND gate. A and B are the input and C is the output. So here this is C is equals to A dot B. And coming to the data flow. What is this data flow? As I said in the data flow, for example, if I have a registers R1, R2, R3, in the previous slide we have discussed what is if I have information which is stored in the register R1 as 0, I just wanted to transfer to the R2. So this data flow can be carried out using the register. So the data flow is the next higher level of abstraction. So previously we have discussed a circuit level, we have discussed a switch level, gate level and data flow. So this is also a higher level of abstraction where you see the transfer of information from one register to the another registers can be carried out. The data can be carried out internally between the registers. So all possible operations on signals and variables are represented here in terms of assignments. So here you can see Y is the output, AB plus CD. So how can we the data, how can see using first is switch level, gate level and data flow, right? So the data flow can be written, that means this expressions can be written with the help of the gate level. So as you observe here, we have the output as Y, AB and get AB, and this is CD, A, B, C, D given as input to OR gate, isn't it? So A, B, C, D. So this is Y. So overall the data flow, the data in the gate A and B and C and D can be transferred to OR gate so that we are getting the output as AB plus CD. Okay. This is what the expressions that the expressions that is carried out with the help of the gates. In other way, as I said as I given you the example between the registers, you can store using flip flops or latches. You can transfer the data between the registers using this data flow on signals and variables in terms of assignments. And coming to the last one is behavioral modeling. So what is this behavioral modeling? Behavioral modeling, this behavioral level constitute the highest level of design description. As I said this is a prominent level in the Verilog as an HDL. Also it consists of the higher level of design description, and also it is essentially at the system level itself. So it is very prominent at the system level itself, but not beyond it. So with the assignment possibilities, looping constructs and conditional branching possible, the design description essentially looks like a C program. So this is in this behavioral level, the syntax or the languages or else the formation of the syntagmatic can be carried out with the assignments which are possible. Looping construct, that means we can see the loops, we can see the conditions, and we can see the description which looks like a C program. So in the C program we see there is the conditions, we see there are the loops, if else conditions, if conditions, and loop, while loop, do while loop. So as such, in this behavioral level we see the assignments possibilities could be of looping constructs, could be of conditional branching, and could be of design description, which exactly looks like a C program. So what is this timing control in behavioral modeling? So in this behavioral modeling, we see some timing controls. So what are those timing controls? Various behavioral timing controls constructs are available in Verilog. So in the Verilog, we could see there are various behavioral timing controls inbuilt. So in Verilog, there are no timing control statements. So in this Verilog, there are no timing control statements. The simulation time does not advance. So as here in this Verilog, there are no timing control statements. So we could see there is no time in advance. The simulation time does not in advance. So the simulation part does not in advance because the timing controls are not available in the Verilog. The timing controls provide a way to specify the simulation time. So what is this timing controls? As the name indicates itself, saying that there is a times to be specified for the simulation process. So the timing controls, it provides a way to specify the simulation time at which procedural statements will execute. So for each and every procedural statements, you could see some timing control statements or the timing controls provided by the Verilog. So there are three methods of timing control we could see while you are executing the program in this behavioral level of modeling. So what are those? The three methods of timing controls are delay based timing control, event based timing control, and level sensitive timing control. So it is very important to remember the different timing controls in behavioral level of modeling. They are delay based timing control, event based timing control, and level sensitive timing control. So using these timing controls, we can see there is specifying the simulation time. We can specify the simulation time at different intervals of the situation. So the delay based, it talks about the delay based timing control, the delays which will be occurring in the execution, in the time of execution, and the event based, the events which are occurring in times of execution. Sometimes the events may occur in between, sometimes events may occur at the earlier stage, sometimes the event may occur at the last stage. So this event based timing control will help us to manifest the timing controls which provide the at the simulation part at the regular intervals of time. So the last one is level sensitive timing control. Sometimes what happens in the specific time, in 1 nanosecond, the execution part may exceed to 10 nanoseconds. Okay, so that means what? Even after executing all the levels, there may be a chance of prolonging, prolonging and procrastinating. All this can be will be monitored using the level sensitive timing control. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.